In our last lecture, we discussed about the path integral, and the expression for path integral is x of f u of t xi is equal to integral dx e to the power I by h cross s, right? So here this s is our classical action and it is given as integral dt of this Lagrangian L. Okay, so and this integration start from 0 to t. Fine. And here in this expression, this integral is over the position only. There is no momentum integral in this path integral expression. Okay, now we want to see the expression of this path integral for a particular system in more generalized form, that is in our phase space. Okay, and in phase space we have the momentum components as well as the position components also. Okay, so to do that, let me start with equation which we already had derived in our last lecture. Okay, so and this expression is given as follows, that is x of f u of t xi is equal to integral multiplication starting from k equal to 0 to n minus 1 dxk, again multiplication starting from k equal to 0 to n minus 1 x k plus 1 minus I t divided by h cross n Hamiltonian x k. Okay, fine. Now as you can see in this equation, this equation is now a linear equation, so it is not difficult now to solve this linear equation. So to solve this equation, first of all we start with this expression. Okay, so let's try to solve this expression first. So for this expression, for this first term, that is the one term, we will have this x k plus 1 and then xk, and we know that this expression is nothing but the Dirac delta function, that is delta of xk plus 1 minus xk, but we also can express this delta function in Fourier space like this, that is integral of momentum p of k divided by 2 pi h cross e to the power I p of k divided by h cross x of k plus 1 minus x of k. Okay, now the next term is this term, and for this term this part is just a constant because it is not the operator part. So here this Hamiltonian is the only operator. So for the second part we will have the equation like this, that is xk plus 1 and this Hamiltonian operator and then xk. Fine, but here notice that this Hamiltonian operator h is a function of both position and momentum. Okay, so now I can write this equation in this way. That is, we also know that the complete momentum completeness theorem or completeness equation, that is integral of dpk divided by 2 pi h cross pk is equal to unity. Okay, so now if I put this expression in this equation, then what I can write? Well, it looks like following. So integral dpk divided by 2 pi h cross x k plus 1 p of k Hamiltonian, and it is a function of momentum and position xk. Okay, but we know that this expression is nothing but e to the power I by h cross p of k xk plus 1. Fine. Now, what is this expression? Let's try to understand this expression little bit. Okay. In this expression here, this Hamiltonian is a function of both position and momentum. So this Hamiltonian can act on this momentum as well as act on this position. But in our classical mechanics, if we say that this Hamiltonian is usually nothing but the total energy of for a system, and total energy is the kinetic energy plus potential energy. So usually we will have the p square by 2m plus our some potential term, right? But in more general, this Hamiltonian can also contain a term like p of x. So these kind of terms are called as the mixed term. Okay, and whenever this Hamiltonian contains the mixed term, then in that case we can say that, well, I can write this expression in this way, that is x of k and this Hamiltonian. Now this Hamiltonian, what we have is no more operator, it is just an algebraic equation. Okay, fine. Now if this Hamiltonian H contains a mixed product like this, then we assume that, well, there must be some certain ordering of this operator, because here this momentum and positions are operator, right? So for example, if we can say that, well, this momentum operator stand left to this position operator. So this is how we adopt, okay, this operator ordering. Or in more general, I can say that we can also adopt a new ordering operator ordering, that is what we call the Wallace operator ordering, and it is nothing but the average over all possible ordering with equal weight. Okay, so I can write this expression as follows, that is xpk, that is pk Hamiltonian, and it is a function of momentum and position of potato obviously, and then xk, and it is equal to pk xk h, right? But here this h can contain a mixed product like this, so I can use the Wheeler operator ordering techniques, so which is nothing but the average over all possible ordering. So in this case we will have half xk plus 1 plus xk. Okay, so let me just denote this term as flowing, that is the x bar k. Okay, so finally I can also write this expression like this, that is, it is nothing but exponential minus I pk xk divided by h cross. Okay, so finally I can write my expression for this. I can write this expression as follows. So finally I can write x k plus 1 Hamiltonian xk is equal to integration dpk divided by 2 pi h cross exponential I by h cross pk x k plus 1 minus xk Hamiltonian, and it is a function of pk x bar k. Okay, so this is how this expression looks like. So now we have this expression and this expression, right? So if you put these two expressions in this expression, then I will get the expression like this, that is x k plus 1 minus it divided by h cross n Hamiltonian hk is equal to integration dpk 2 pi h cross exponential I by h cross pk x of k plus 1 minus xk, and then bracket 1 minus I t divided by h cross n h p of k x prime of k. Okay, fine. But here this t by n is nothing but the delta t. Okay, so when this n tends to infinity, then this delta t tends to 0. Okay, so in this situation, when in these situations we can also write expression like this, that is, if we have a equation like this and here this epsilon is a very small number, then I can write this exponential or expand this exponential like this, that is 1 plus epsilon dot dot dot. Okay, so I can ignore this higher order term in this case if this epsilon is very less than 1. Okay, so similarly, if I choose this small number epsilon as this expression, that is minus I by h cross delta t h of pk x bar k. Okay, so as here this delta t is delta t tends to 0, that means this epsilon is actually a very small number. So I can write in this case 1 plus epsilon, which is nothing but 1 minus I by h cross delta t h p of k x bar of k is equal to exponential minus I by h cross delta t h p of k x bar of k. Okay, so if I put this expression in this expression, then I will get the following. So finally we will have the x k plus 1 minus I delta t divided by h cross Hamiltonian xk is equal to, so here h at delta t tends to 0, so we should have at the limit delta t tends to 0, we have the integral dp k 2 pi h cross exponential that's perfectly fine. But for this expression we have our this expression. So in this expression I can take delta t, then I have to divide it by a delta t term. So p of k x k plus 1 minus xk divided by delta t, and then for this expression, for this quantity we have this expression, so it is nothing but minus, so we already take out this term, so we only have the Hamiltonian term inside the bracket. Okay, so h of pk x bar k bracket inside this exponential term. Fine. So now I can put this expression in our most initial equation, that is this equation. Okay, so if I put that equation in this equation, then after this integration we will find the actual path integral in phase space. Okay, so if I do that, I will get the following expression. So let's do that. So we have our final, the transition amplitude or path integral expression is x of f u x of I is equal to integral multiplicative symbol from k equal to 1 to n minus 1 dxk multiplicative symbol from k equal to 0 to n minus 1 and this expression, but this expression is nothing but this expression, right? So let me just copy it and paste here. But now I can take out this limit, so this gives me delta t, sorry, limit delta t tends to 0, integral multiplicative symbol, that is from k equal to 1 to n minus 1 dxk. But here this multiplication is on this momentum as well as acts on this exponential. Okay, so I can write this expression like this, that is the multiplicative symbols from k equal to 0 to n minus 1 for this expression, that is p k divided by 2 pi h cross. And when this multiplicative symbol acts on this exponential, the exponential term summed over. Okay, so we will have the exponential I by h cross delta t summation k equal to 0 to n minus 1 pk xk plus 1 minus xk divided by delta t minus h, and it is a function of pk xk like this. Okay, but here we denote the integral, this expression, the integral of this expression, that is the multiplicative symbol starting from k equal to 1 to n minus 1 dxi as d of x, and the integral of this multiplicative symbol starting from 0 to n minus 1 dp of k divided by 2 pi h cross h, the integral dp. Okay, and for this expression, in this expression when at the limit delta t tends to 0, this expression becomes, that is xk plus 1 minus xk divided by delta t is nothing but our differentiation. So we will get the x dot, and this is a function of t of k. Okay, also we will get an expression from this expression itself. So if I choose this expression as a function, then I can write something like this: if delta t is very small and we have the expression like this, that is summation k equal to 0 to n minus 1 and some arbitrary function f of tk, then I can express, or I can write this expression like this. So it becomes integral, this summation becomes integral starting from the time to 0 to t d tau d f of tau. Okay, so if I put all this kind of expression and this expression in our final expression, that is this expression, we'll get the equation like this, that is x of f u x of I is equal to integral d of x integral d of p exponential I by h cross integral 0 to t dt momentum x dot minus Hamiltonian, and it is a function of position and momentum. Okay, fine. So this is our final expression for the path integral in phase space, because here this integral is over the position and momentum. Okay, and this path integral actually extend over all function of momentum and in momentum space and all function of position in coordinate space. Okay, fine. But here you can notice that in this exponential expression, this term, this term looks like a Lagrangian equation, because in our classical mechanics we have the Hamiltonian H equal to summation P Q dot minus L, right? But here in this case H is obviously a function of momentum and position, but here Lagrangian is function of position and the dot Q dot. Okay, but in this case, though it looks like a Lagrangian term, but actually it is not the Lagrangian, because here this term is a function of position and position dot as well as the momentum also. But why momentum? It is because we don't know the exact expression for this Hamiltonian, right? What does it means? That this Hamiltonian may contain a mixed term. Okay, so in usually we have the form for the Hamiltonian is p square by 2m plus some potential term like this, but in this case there is no mixed term, but we can also have an expression like this. So this is the mixed term, and this position and momentums don't commute to each other. So whenever we have a mixed term, then it means that the Lagrangian which we can construct from this Hamiltonian cannot be a function of q and q dot only. Okay, so it is a function of q dot and momentum also. So we can say that this expression is not exactly the Lagrangian. Okay, and now in our next class we'll discuss that whenever we take a special case of the Lagrangian, that is special case of the Hamiltonian, that is for the case when there is no mixed term. So in that case we have p square by 2m px. So if we have the Hamiltonian of this form, then if you put this expression here and after calculation we will actually get the expression like this that we already had derived in our first class. This expression we will get. Okay, so here there is no momentum integral. Okay, so whenever we choose a Hamiltonian or of this form, then we in our path integral we don't have this momentum integral. It already integrated or calculated explicitly, okay, or it already carried out explicitly. Okay, fine, that we will discuss in our next lecture.